Hi, today I'd like to talk about rotating a vector. And what we have here is a vector depicted in three-dimensional Cartesian space. We have, with this representing the x-axis, this line representing the y-axis, and the vertical line representing the z-axis. Okay, and here we have our vector. It has a length of r, and if we were to draw projection down from the vector onto the xy plane, then the angle between the x-axis and that projection, we can call that theta, and the angle between that projection on the xy plane to the vector itself, we can call that phi. And so now we can also depict the vector as x, y, z. And so now, if we look at this vector here, okay, we know that if phi is equal to 90 degrees, then cosine of phi is going to be 0, and we know that x and y will be 0 regardless of what theta is, okay? And if phi is 0, then cosine of phi is 1, and again, in this case, the x will be just r cosine theta, and y will just be r sine theta. So we know that both x and y will be some multiple of cosine phi. Okay, so we'll go ahead and write that out. So we can say x is equal to r cosine theta cosine phi, and we know that y is equal to r sine theta cosine phi. And if we look at z, we notice that theta has nothing to do with z, okay? And when phi is 90 degrees, then it's exactly equal to 1 times z. So we know that z is just the radius times the sine of phi. So z is equal to r sine phi. So now what we're gonna do now is say what happens if we rotate this vector depicted here around the z-axis. So basically all of the movement will be parallel to xy plane. Okay, so let's say if we decide to rotate it by an angle of alpha, then the easiest way to depict that is to essentially substitute alpha or theta plus alpha for theta. Okay, so in this case now we can say x prime, and x prime is going to be essentially the new x after it's rotated. It's going to be r cosine theta plus alpha cosine phi, and y prime, okay, the new y, is going to be r sine theta plus alpha, okay, cosine phi, and z is equal to, again, just r sine phi, because again it has nothing to do with theta or theta plus alpha. Okay, so z prime, okay, the new z is going to just be r sine phi. Okay, so now let's go ahead and work these out. Okay, so we know now that x prime is going to be r times cosine theta cosine alpha minus sine theta sine alpha, and that's just basically cosine theta plus alpha, okay, times cosine phi. Okay, so in this case now we can say x prime is equal to r cosine theta cosine alpha cosine cosine phi minus r sine theta sine alpha cosine phi. So now we know that now r cosine theta cosine phi, okay, that's equal to x. So x prime, okay, again now we have r cosine theta cosine phi, so that's just equal, that part is equal to x times cosine of alpha minus, okay, now we know that r sine theta, okay, cosine phi, that's y, so that's just minus y times sine alpha. And since we're doing this in three-dimensional, well, we have to do it, we have to give it a z component, so I'll just say plus 0 times z. Okay, so we know that's the equation for the for basically what the new x is. Okay, so now let's go ahead and find the new y. Okay, so we can say now, which is y prime. Y prime is equal to r, okay, in this case now, we know that sine theta plus alpha is going to be sine theta cosine alpha plus sine alpha cosine theta times cosine phi. Okay, so now y prime is equal to r sine theta cosine alpha cosine phi plus r sine alpha cosine theta cosine phi. So now we know that in this case r sine theta cosine phi, well, that's y. Okay, so we can say y prime is equal to y cosine alpha plus, now in this case now we know that cosine, okay, r cosine theta cosine phi, that's x, so that's plus x, okay, sine alpha. So now I'll just rewrite it and say y prime is equal to x sine alpha plus y cosine alpha plus, well, I need to put in the z component, plus 0 times z. So now we got the new y. Well, we know that z prime hasn't changed, so that's easy. So we can say z prime, and again, since we have to put it in a three-dimensional coordinate, is equal to 0x plus 0y plus z. And so now I can write this in matrix notation. Okay, so we can say now x prime, y prime, z prime is equal to the matrix now, which is cosine alpha minus sine alpha 0, and we're going to get sine alpha cosine alpha 0, and we have 0, 0, 1 times the vector of x, y, z. So now what we've derived here is basically the rotational matrix, which actually is a type of operator because it operates on this vector, okay, to give you that vector, okay? And what it does in this particular case is that it rotates it through the angle alpha about the z-axis. So let's go ahead and find an example, okay? So let's say now that we have the angle, or we have the vector, okay, 1, 0, 0. And that's basically a vector that's 1 along the x-axis, 0 along the y, 0 along the z. Okay, so it's just basically a vector right here, and we're going to operate on it with this and see what happens. Okay, so I will go ahead. Okay, we have cosine alpha minus sine alpha 0. We've got sine alpha cosine alpha 0. We have 0, 0, 1. So whenever we operate on a vector, we take the first component here, okay, the product of these two components plus the product of these two plus the product of these two, and that becomes the top one. Then we'll take the product of these two plus the product of these two plus the product of these two, that becomes the second. And we do basically the same thing to get the third. Okay, so let's see what we get. Okay, so let's assume that we're going to rotate 90 degrees. Okay, so now cosine of 90, okay, that is 0. Okay, so 0 times 1 is 0 plus 0 times 0, that's still 0, plus 0 times 0, that's 0. So now sine of 90, that's 1 times 1, that's 1, plus 0 times 0, that's 0, plus 0 times 0, that's 0. So 1 plus 0 plus 0, that gives 1. And again now, 0 times 1 is 0, 0 times 0 is 0, 1 times 0 is 0, so that's 0. So what we get is the vector 0, 1, 0, which is essentially the unit vector along the y-axis. So basically, the vector started off here, and we rotated it 90 degrees, and it ended up here. So we just did that. Okay, so that proves that it does rotate that 1 to 90 degrees. Now let's pick another vector. Okay, this time, okay, we're gonna have a vector here, okay, that is 0, 0, 1. Okay, and that's basically a unit vector along the z-axis. Okay, and we're going to operate on that by rotating it along the horizontal plane. See what happens. Okay, or shall I say around the vertical axis. Okay, so again we have cosine alpha minus sine alpha 0, sine alpha cosine alpha 0, 0, 0, 1. Okay, and again we're going to use the same method to operate on this vector here. Okay, so again, cosine of 90 degrees, that's 0 times 0, that's 0. Okay, plus 1 times 0, that's still 0, 0 plus 0 is 0, and 0 times 1 is still 0, so the top one is 0. Let's go to the middle one. Okay, 90 sine of 90, that's 1 times 0 is 0, plus 0 times 0 is 0, plus 0 times 1 is 0. Add them up, we still get 0. Again, we got 0 times 0, 0 times 0, 1 times 1. Add them up, we get 1. Okay, so now what is interesting about this one is that we started with that vector and we ended up with the same vector. Okay, so exactly what happened there? Well, when I said this matrix here represents the act of rotating the vector. Okay, so if I have a vector here, this pencil representing a vector, okay, and this represents the act of rotating it. Every time I operate on it, I rotate it through some angle. Okay, just like that. Okay, so now with 0, 0, 1, that means now the pencil is sticking straight up. Okay, now if I rotate it again through the horizontal, it's still standing straight up. Okay, and I can do that indefinitely and I'll still get the same. Okay, in this case, when you have a vector that you operate on and you get a scalar multiple of that same vector, and in this case, not all cases, this case, that scalar multiple happens to be 1, then this vector is what we refer to as an eigenvector. Okay, And what eigenvector represents is some kind of invariant quality, or basically something that does not change. Okay? So now, granted, when we talk about vectors, often, most of the time, people refer to the spatial concept of a vector. But however, a vector is much more than just that. A vector is essentially a way to structure information, okay, where you have features and the parameters. So in this case, in the case of a spatial vector, the feature represents each axis in the coordinate system, regardless of how many dimensions it is. Okay, and the parameter is the actual length along that axis. Okay, for that makes up that component of the vector. However, for other fields such as machine learning or artificial intelligence, often the input information is structured as a vector of features and parameters, which the algorithm essentially operates on to get the desired result. Another case where vectors are used, or the concept, and granted this requires a great deal of modification, but what I'm just trying to get is just a very basic concept, is in the field of quantum mechanics, where the state of a system is represented by a vector in an infinite dimensional space, which they call Hilbert space. Okay, and the operator represents observable quantities such as the Hamiltonian, which acts like energy, or momentum, okay, or things like that. Okay, and often when something is measured, it's driven into what we call an eigenstate, which essentially can be conceptualized as a form of eigenvector of that operator. Anyway, that is all I have for now. I hope you find this very informative, and I'd like to thank you very much for